Hello, my name is Saptashwa Bhattacharjee. My roll number is 21EC10064. I shall be presenting my bachelor's thesis project 2 on the topic novel radiation hardened cross-coupled voltage control oscillator in the SCL 180 nanometer technology. So let us first discuss the impact of radiation on the operation of electronic circuits. So circuits, when operated in space, are exposed to radiation. The radiations contain ions like protons and electrons, which are trapped in the Earth's magnetic field. These radiations can also be cosmic rays in the outer space. Now, when these high energy radiations strike against the active region of transistors, let's say the drain region of NMOS and PMOS, then electron and hole are generated due to the impact. So let us see what happens when there is a radiation strike at the drain of NMOS. The drain body junction in an NMOS is reverse bias. So when excess electrons are generated, they swiftly move towards the N plus drain region, and the holes are swept towards the p-type substrate. As a result of this, the drain current of the NMOS increases. Similarly, when there is a radiation strike at the drain of PMOS, the newly created electrons are drawn towards the N-type substrate, while the holes are directed towards the p plus drain. This again increases the net drain current flowing out of the PMOS. So in either case of NMOS and PMOS, a radiation strike increases the drain current. Now to capture the impact of a radiation strike on the operation of a circuit, let us see its impact on a node which is undergoing transition either from 0 to VDD or VDD to 0. Over here, we have taken the example of a CMOS inverter. So let us say that the output node is going from 0 to VDD. So in this scenario, the PMOS turns on and the NMOS turns off. So if there is a strike at the drain of the NMOS, then it will be fatal for the circuit, since this NMOS will not allow the Vout node to go up to VDD. Similarly, when the Vout transitions from VDD to 0, it is the NMOS which turns on and the PMOS which turns off. So in such a scenario, if there is a strike at the drain of the PMOS, then it will cause high amount of current to flow through this output node, and it will not allow the output node to settle at 0. So each of these cases can be emulated in simulation by either pulling a current from the node Vout or injecting a current at the node Vout. So the worst case impact of strike is when we pull current out of a node when it is undergoing a transition from 0 to VDD, or when we inject current into a node when it is undergoing a transition from VDD to 0. The overall phenomena of a radiation strike on a circuit can be modeled using the double exponential current pulse, wherein I0, alpha, beta, and Q total are fitting parameters. The value of these parameters have been mentioned in the reference specified over here. Now for the TSMC 180 nanometer process, the value of these parameters are given over here. Q total is 1 picocoulomb. I naught is around 5 milliampere, and alpha minus beta is roughly 200 picosecond. So this complex double exponential current pulse can be rather replaced by a simpler version wherein a constant current of 5 milliampere flows for a 200 picosecond duration, which ensures that a charge transfer of 1 picocoulomb happens during this radiation strike. Now to capture the effect of strike during simulation, we come up with this strike circuit, wherein we assume that our circuit has differential outputs, Vout plus and Vout minus. So whenever there is a VDD to 0 transition in the Vout minus, it means that in the positive output Vout plus, there is a 0 to VDD transition. So we detect the rising edge of the Vout plus, and we convert that into a current pulse of magnitude 5 milliampere for a duration of 200 picosecond, and we inject this current pulse in the Vout minus node, which is undergoing a transition from VDD to 0. This brings out the worst case impact of strike, as was mentioned in the previous slides. Now, the literature survey has revealed that most of the prior works, which targeted at designing radiation-hardened voltage-controlled oscillators, used triple modular redundancy-based approach, wherein 3 copies of a VCO were placed in parallel and the outputs were fed to a majority voting gate. This design is able to tackle a radiation strike at any of the internal nodes of the VCO or at the input of the majority voting gate. However, it fails to provide radiation tolerance if there is a strike at the output of the majority voting gate. Some literatures have also used differential cascaded voltage switching logic, DCVSL logic, because it has a good ability to resist the single event effect. Now let us begin our discussion on the design of an unhardened quadrature VCO. So a quadrature VCO means that it has got 4 stages. Since the phase difference across the loop is 360 degrees, it means that the phase difference across each stage is 90 degrees. Let us say that the delay of each stage is tau. So the frequency is roughly 1 by 8. Now in a VCO, this delay is made a function of the control voltage. Now this is the structure of a delay cell wherein we have a latch, which is a cross-coupled inverter pair. This behaves as a latch. The on resistance of these MOSFETs, MP1 and MP2, are controlled by V control. So they are operated in the triode region and their on resistance are controlled by V control. But since their on resistances are governed by V control, it means that the delay associated with the nodes Vout plus and Vout minus are also a function of V control. So the frequency of oscillation is a function of V control. This is the table which gives the relation between the relative dimensions of the different MOSFETs. We have assumed a 1.5 ratio between PMOS and NMOS, which is the ratio of their mobilities of holes and electron. Now for the previous architecture, the only variable is WNMOS. So we have plotted the variation of jitter in the differential output with the width of the NMOS, and this kind of a graph is obtained. So as we can see that as the dimension of the NMOS increases, the jitter reduces, but it also amortizes as WNMOS is increased more and more. It fairly becomes constant. So for simulations, we have chosen WNMOS to be around 33 U, for which jitter of roughly 35 picoseconds obtained. This is the eye diagram of the differential output in the absence of a radiation strike for the chosen value of WNMOS and V control 900 millivolt. This slide brings out the effect of light on this VCO architecture. So as we can see that the eye diagram shows a lot of jitter upon a radiation strike. And this diagram brings out the transient response, showing the impact of strike on the Vout minus node. So this architecture is not at all tolerant to regression. So we move on to the next architecture. The philosophy behind coming up with this architecture is the fact that multiple radiation strikes in a circuit at a particular point of time is a very low probability event. The probability of having multiple strikes in a circuit at a given instant is less than 10 to the power minus 7. So we have split each delay cell into n parallel branches. So there will be strike on any one of the branches and not multiple branches at a given point of time. Now also used resistors which ensure that proper DC operating points are established at the output of each node. So in this architecture, the variables are N split, the resistance R, and the WNMOS in each of the delay cells. So we have to come up with a combination of N, R, and W NMOS which ensures minimum jitter upon a radiation strike. So at first we fix a value of N and we plot jitter as a function of W NMOS for different values of. So for a given value of N, we choose a pair of W NMOS and R for which the jitter is the minimum. And we repeat the same process for different values of N and choose the value of N that is the lowest jitter among all the cases. So this is a plot of jitter versus W NMOS for different values of R for different values of N. We have taken 4 different values of N, 5, 10, 16, and 20. And this is the table where each entry shows the combination of W NMOS and R for which jitter is minimum for a given value of N. So we have chosen N equal to 16, W NMOS 1.9, and R to be roughly 5.6 kilo ohm for which the jitter is 7.6 picosecond, that is less than 10 picosecond. And this is the corresponding eye diagram upon a radiation strike. So although there have been improvement in the eye diagram, the jitter has been reduced, but still this is not acceptable. So we go on for further iteration. The basic philosophy is kept the same. Here as well, we split each stage into n parallel branches, n parallel delay cells. We have kept the coupling resistor R, which ensures proper DC condition. But this time we use capacitors in parallel to the resistors. So let us say that there is a radiation strike on one of the delay cell. And we have already said that 1 picocoulomb amount of charge gets deposited at the node or gets pulled out of the node as a result of the strike. So these capacitors share charge among each other. Charge sharing happens between these capacitors and the effect of strike is minimized. So the effect of strike gets averaged out by a factor of n. So every delay cell is coupled using an RC network. This RC acts as a filter and also these capacitors. They share charge among each other to reduce the impact of strike on a particular branch. So analog summation and averaging are achieved by charge sharing between the n capacitors in each stage, which was not present in the previous architecture. So in this manner, the effect of strike on any one of the branches gets suppressed by factor of n, where n is the number of splits in each branch, in each stage. So in this architecture, the parameters are N, C, R, and W values. So we have to choose them in a way that the jitter in the output is minimum. Now we note that this resistance R is only for the purpose of establishing a total DC condition. So we choose R equal to 100 kilo ohm without loss of generality. And we choose a particular value of N, say N is equal to N1, and plot the jitter versus W NMOS for different values of C. So we choose that value of W NMOS and C for a given value of N such that the jitter is minimum. Let's say the values be C and NMOS N. Now we repeat this process for different values of N and we choose that combination of N, C, and W NMOS, which is the global minimum of jitter. These are the parametric simulations where for different values of N, we have plotted the jitter versus W NMOS for different values of C. Again, we have simulated it for 5 different values of N. And this table summarizes the value of W NMOS, C, and R corresponding to each value of N, which leads to the lowest jitter. We choose this particular combination, N equal to 16, W NMOS equal to 1.8, R is 100 kilo ohm, C is 35.52 femtofarad, and it leads to a jitter of 7.6 picosecond. This is the plot of jitter with control voltage. As we can see that there has been significant reduction in jitter, the maximum jitter being around 8 picosecond. Variation of frequency with control voltage. This is the characteristic of the VCO, the maximum attainable frequency being around 3.4 gigahertz and the minimum being around 1.1 gigahertz. This is the eye diagram of the differential output in the presence of strike. So as we can see that in this case, the eye diagram has been significantly improved as compared to the previous case. Here we present a comparison of the eye diagram of the output in the absence of a strike Eye diagram of the output when there is a strike on the unhardened VCO, which was our first architecture, and the impact of strike on the differential output captured through the eye diagram in the case of our latest architecture, which is RC coupled quadrature VCO, which we also name as the hardened VCO. These comparisons are at the schematic level. So our proposed scheme performs quite well in mitigating the impact of radiation. Now, after the schematic level analysis, we move on to the layout level analysis. So the layout of both the hardened and unhardened VCO has been designed in SL 180 nanometer technology node and has been integrated with input-output pads. So the core consists of both the unhardened VCO and the hardened VCO. The dimensions of the hardened VCO, that is the RC coupled quadrature VCO, are mentioned, and same for the unhardened VCO, the dimensions have been mentioned. So the RC coupled quadrature VCO occupies around 8.76 times more area on silicon, which can be attributed to the large area occupied by the coupling capacitors and resistors in each stage. This is the frequency versus control voltage plot of the RC coupled quadrature VCO in the TT corner at 27 degrees Celsius at the post layout level. So the maximum frequency attainable at the post layout level is around 900 gigahertz and the minimum is around 300 gigahertz. So we see roughly around 3.5 times reduction in the maximum attainable frequency as compared to the schematic level. This is due to the parasitics arising out of the metal interconnects. Now, to make the simulations more realistic, we also include the impact of process variations. The effect of process variation is on the mobility of carriers. For example, a fast slow corner means higher than average electron mobility and below average hole mobility. Also, the RC coupled quadrature VCO has been tested over a wide range of temperatures from minus 40 degrees Celsius to 120 degrees Celsius. To combine the effect of temperature and process variation, we use FF corner at minus 40 degrees Celsius and SS corner at 120 degrees Celsius. So mobility is higher at lower temperature. Also, the mobility is highest in an FF corner. So FF corner at minus 40 degrees Celsius will imply the highest carrier mobility. And since mobility reduces with temperature and mobility is least in an SS corner, so SS corner at 120 degrees Celsius will correspond to the lowest carrier mobility. So FF corner at minus 40 degrees Celsius, since it has the highest carrier mobility, will also yield the maximum frequency range. Similarly, SS corner at 120 degrees Celsius will yield the minimum range. This has been affirmed by the frequency versus control voltage plot in either of the cases. In FF at minus 40 degrees Celsius, the maximum attainable frequency is higher than the nominal value. It's 1.2 gigahertz. While in case of FF at 110 degrees Celsius, the maximum attainable frequency is around 620 gigahertz, which is lower than the nominal value. This is the comparison of the radiation performance at the post layout level. So as we can see that there is negligible impact of strike on the hardened VCO, that is the RC coupled quadrature VCO at the post layout level. So there is around 75 to 80% improvement in radiation tolerance as when jitter is compared. So our proposed design works fairly well. Following are the list of references that have been used in preparing this material. Thank you.